Have you ever wondered what would happen if centripetal force went on strike? Without centripetal force, orbital mechanics would cease to exist, meaning no satellite TV, no internet, no GPS. The world would be quite a mess. So how does this awesome concept that is so important to keeping our world in one piece work? Or better yet, how does it work when applied in orbital mechanics? Well, before we get into centripetal force, let's remind ourselves of another concept, one that's usually associated with falling apples. Gravity. Gravity is the invisible force that keeps you and me attracted to the ground. Sir Isaac Newton realized that two bodies will always attract each other. The bigger the object, the greater that attraction. He described this relationship with a formula. By taking the mass of the two bodies and the distance between each other, the result equals the force of gravity between the two, expressed in acceleration. For example, on Earth, the acceleration at the surface is approximately 9.8 meters per second squared. In other words, if the ground were to suddenly give out, we'd all fall at a speed constantly rising by 9.8 meters every second. This is very important, and we'll use it later. Without gravity, life would be quite an amusing story. Unfortunately, gravity also makes getting into space very difficult. Because the Earth is constantly pulling us back, a rocket would have to be constantly pushing in the opposite direction. This rocket would require an infinite amount of fuel though, which is just not feasible. But luckily, centripetal force opens up a new door. Centripetal force is just the amount of force required to keep an object going in a circle instead of a straight line. In fact, the formula for centripetal force is actually just a modified version of F equals ma. This equation describes the force of an object that is accelerating in one direction. All we have to do is change the a, the acceleration variable, to something that will describe motion in a circle. But how do you measure the force if the object is never accelerating or decelerating? Well, remember that velocity doesn't equal just speed, but also direction. When an object is traveling in a circle around another body, the object may be traveling at the same speed, but it will be constantly changing direction. After all, it's going in a circle. Therefore, Newton came up with an equation to describe this change, or acceleration, in the velocity's direction. Using simple geometric rules, you can create a triangle using the velocity vectors created by an orbiting object. A vector in relation to velocity is a line segment indicating speed by its length and direction with an arrow. Take this situation for example. A small spacecraft is orbiting an Earth-like planet, traveling at velocity v. If we cut a small chunk out of the circle created by its orbit, we can draw vectors that relate to the spaceship's velocity at two different times. By finding the change between these two vectors, we can find the change in velocity, or the acceleration, which is our final goal. First, we remember that the change between two things is found by subtracting them and dividing the result by time. So, if we start with 4 apples, and a second later end with 1 apple, our change was minus 3 apples per second. Similarly, we can subtract two positive vectors 1 second apart by adding the second vector to the negative of the first vector. The result is our change in velocity, or delta v. Finally, we can divide the delta v by the time between the two vectors, just as we did with the apples. The time between the two vectors can be expressed as a change in time, or delta t, times the speed, revealing a final equation of delta v divided by delta t times velocity. But this leaves us nowhere closer to getting what we need, does it? Well, it actually does. There is just one small key factor that we're missing. Notice that when we put the two vectors tip to end, the angle we create is exactly the same as the angle of the two radii of the chunk of circle we cut out. Because of this fact, we can use some geometry rules to show that the base of the first triangle divided by the base of the second triangle will equal one of the sides of the first triangle divided by the corresponding side of the other triangle. We already found out base sub 1 divided by base sub 2, delta v divided by delta t times v. Filling in the other side of the equation, we get the velocity of the second vector divided by the radius of the orbit. Finally, we multiply v for both sides of the equation, and we find that the acceleration of the orbit due to the change in direction is equal to v squared over r. By substituting this in for the acceleration in F equals ma, we have found the force required to keep an object in orbit, or centripetal force. You can think of this force like a rope. If you're swinging your friend round and round on a rope, you need to be able to hold on tight enough to make sure your friend doesn't go flying into the ground. We have one final problem though. Where do we get the necessary centripetal force to keep a rocket in orbit from? Another rocket? A genuinely long rope? Wait a minute, we have gravity. Gravity acts just like a rope that's constantly pulling us downwards, exactly what we need. Unfortunately, we cannot change how much force gravity exerts on the rocket except by changing its orbital height. But we can change the rocket's speed, and therefore how much force gravity needs to equal. On paper, it looks like this. The force of gravity needs to equal the centripetal force needed for the certain object in orbit at a given height. What we really need to solve for in this entire equation is for v, how fast our rocket needs to be traveling. Using simple algebra, we can rearrange the equation to suit this need, and we get velocity equals the square root of the gravitational constant times the mass of the planet divided by the radius of the orbit. Notice that some variables canceled out. Now we can input some values. The height of the orbit would be determined by the manufacturer, but let's say that the orbital height is roughly 413 kilometers above mean sea level, approximately that of the International Space Station. We will also use the known mass and radius of the actual Earth. Finally, we use the gravitational constant discovered by Isaac Newton for g. This gravitational constant is a number that remains the same throughout the universe. You can think of it like pi, but for gravity. Solving for this equation using these numbers reveals that the necessary speed of our rocket or station will need to be about 7.5 kilometers per second. And guess what? The average speed of the ISS is 7.66 kilometers per second. Furthermore, because there is no air in space, and therefore no drag to slow you down, once you reach the desired speed, there is no need to fire your rockets ever again. To further help visualize the concept of centripetal force and orbital mechanics, we can use a simulation. In this case, we have a small rocket climbing up to its desired orbital height. The next step would be to execute a burn parallel to the ground in order to achieve a high enough velocity to obtain a stable orbit. The simulation doesn't tell us what that speed needs to be though, so we'll have to calculate it ourselves using our formula. With an orbit height of 80,000 meters above the surface, and a planet mass of 5.292 e22 kilograms, we get a required velocity of 2,280 meters per second. Once our rocket reaches the top point of its current trajectory at 80,000 meters, or in orbital terms its apoapsis, we burn until our speed indicator reads the desired number. Even real spaceships follow this same technique, just with some more fluidity and of course much more precision. For example, most spaceships and satellites that wish to orbit the real Earth acquire the necessary speed and altitude all in smooth, consecutive burns instead of separately as we're doing here. Now that we've generated enough thrust to get us up to our desired speed and stop the burn, we can take a look at our overall trajectory. Notice that we are now following a circular orbit with a low point, or periapsis, of about 80,512 meters, and an apoapsis of about 80,905 meters. Not only have we seen how centripetal force applies in orbital mechanics, both mathematically and physically, but we've also discovered a concept we experience every day. In roller coasters, centripetal force is used to make sure people don't fall out of the cars when going around a loop. In racetracks, centripetal force is used to calculate the necessary inclination of the track to make sure cars don't flip over when going around a sharp bend. As for space though, centripetal force is just the beginning. The first step was getting man into orbit. The next was to the moon. Hopefully our next journey will be interplanetary. But whatever our next achievement in space may be, I can assure you, it will use orbital mechanics and centripetal force. Otherwise, it's going to be a very sad journey.